Hello, welcome to the Machine Learning at Home. Today I will show you the small but useful life hack. For example, you want the dimension reduction. The dimension reduction with so-called summon mapping. So summon mapping is called from library MASS. So first of all, we should type it. This library must be installed by default with R, so you should not install it separately. Everything is fine. And then we should use some data for demonstration of summon mapping. For example, iris data. And we typically remove the last column, which is number 5. Summon mapping works only with distances, so we should calculate distance first. Everything will be by default, and from that distances we should take this summon approach. The function is summon, and as a result I want not just numbers, but I want to plot it. So I will take point part from summon mapping, points, and plot them with command plot. And I will use some colorizing. So COL equal to iris. It's the same fifth column pieces. So this is my code. Looks like normal. Let us run it. Unfortunately, as you see here, there are two identical rows in iris data. Row number 102 and 143. This is unfortunate because summon does not allow rows to be identical. Otherwise, distance starts to be 0 and summon does not operate. How to avoid it? There are two ways. And the first way is my life hack, which I like to show. Let us repeat the same line of code, but we will add very small number to the distance. So after the distance, we will make a plus and we'll insert a very small number, 1 by 10 in minus 9th degree. Okay, now summon will operate not exactly with distances, but with distances to which that very small number is added. And let us see what is going on. Yes, everything went absolutely without problem. So you see, this small life hack will allow you, for example, to see how methods which do not normally allow something will work anyway. And another possible solution, of course, is to remove one of two identical rows. So for that reason, we need to have some unique function. So to compare our two-dimension reductions, I will insert command device new, div new, so that will be new device now, and we'll plot into that new device exactly the same line, but again change it slightly. So we will change it in such a way that only unique rows of iris will come into distance function. So many parentheses here, but I hope you understand it. So we take iris data, then we remove identical rows, then calculate distances, then make summon dimension reduction, and then plot it. So let us do it. Okay, and now look what is going on. So this is important to understand, so that our both mappings are very similar to each other. I bet you don't find differences straight away. There are slight differences. I will show you. Here and here dots are slightly differently located. And on our second plot, the actual number of dots is 149, one less. And on our first plot, the number of dots is 150. So there are slight differences, but it does not change the principal appearance of dimension reduction. So that's exactly what we want. Dimension reduction is an approximate technique. and that methods work quite well. Anyway, both solutions will change data slightly, so I don't think they are very different in that way. Okay, so this is how to work, for example, when method does not allow identical rows, but you want to use it anyway. Let us show another example. So let us load my package, and then we'll calculate something simple that will be clusterization. So we'll use k-means clustering and the same iris data without column number 5, and for k-means we typically specify number of centers, and it's also useful 3 centers because we have 3 species. At least we want to have 3 species. And for k-means is useful to specify number of starting points, and start at least 5 in that case. So, and we should also write it in some variable, and I want only cluster data, so I will use cluster part of result, and we'll keep it inside variable iris cl. So everything is absolutely normal. This is a typical example of k-means clustering. Okay, and then I want to use my misclassification function in a slightly unusual way. So misclass, we use clusterization results and also the species data from 5th variable. And because clustering does not know species names, instead of species names it will give us some numbers. So I will use my option best equal to true. This will find some best arrangement in relation between species and cluster numbers. I want also save my misclassification table into RES variable. So misclassification is not bad. As you see, 10%, 11% of misclassification error. But what I want to do, I want to apply some statistical testing to the table. For example, tables of that sort are recommended to analyze with McNamara test. And that test will kind of check for randomness. Let us see if it works. Unfortunately not. Unfortunately, p-value is not supplied. This is because there are zeros in, for example, setosa column. And how to avoid these zeros? Again, add the small number. Let us make this small life hack. Plus 1e minus 9. 1 multiplied by 10 in minus 9 degree. It's a very, very small number. And now p-value is here, and of course p-value is significant, which means that this table is not random, so there is some structure of misclassification, exactly what we see with our own eyes. But this is now supported with a p-value. Some people will need it. So this is how to use small number, for example, in cases when the test does not allow zeros in the cells. It happens with the chi-squared test quite frequently. So this is again a life hack, how to use the very small numbers for multiple different purposes. I hope you will find it useful. Thank you very much.